This is the only study?
Yes, we should also change that.
All right, we're on air. We have Hossein Movasati talking about the variational Hodge conjecture and Hodge loci.
Okay, thank you for inviting being here, organizers, everyday working. Okay, so I have prepared 5 pages. I think I have to skip many details. Okay, so let's first of all the whole part with our complex numbers, and okay, and then I will take family. Varieties, and anyway, the fibers will be denoted with xt. They are in the same projective space, and so this will be the fiber. And let's say I will just fix a variety and a fiber over, let's say, a point, and the point I will call it 0. And then sometime I am not interested in variation, I will just call this fiber x. So x, x0 is the same. Maybe I have to call this one holographic x. And okay. I think last week there was a few talks, or at least the Tony Scholl's talks appeared. So the Hodge cycle is basically, maybe I write okay, something also maybe with fixed notations. I mentioned xp will be n, and I will be just interested in the middle cohomology. So, and since I'm talking about Hodge cycles and so on, I will assume that n is even. For some reason, I don't know, I will not use n equal to 2k, I will use n over 2. My notation. So at the end of the day, what is Hodge cycle? We will take this so HNX0 complex number. Actually, I will use its their own cohomology version. So by Hodge, it is known that this guy has a Hodge decomposition. In particular, in the complex side, you have this subspace. From another side, you know that cohomology with rational coefficient inside here. So you're intersecting cohomology with rational coefficients with this piece of Hodge decomposition, and you call the cycles there the Hodge cycle.
Can I ask before we go further, is there material published or online or somewhere?
No, this is exactly, this is the article is basically called the Hodge cycle for
Can you write the
so the paper called a Hodge algebraic for cubic hypersurface. But I warn you that there is no proof. A lot of computations, and by computer, I indicate how you can recover the codes and so on. It's a kind of experimental mathematics.
is it online or?
This is online. This is already an archive.
So if I search for that.
Yeah, exactly. Anyway, let me go further. So, so the well-known is the Hodge conjecture at the end. This Millennium conjecture says that if you take delta must be a subword of an algebraic cycle, and z must be ni rational number. The I, as I said, I will focus on the middle dimension. So for the dimension in 2 algebraic cycles in X. Okay, So let's go further. And I think this is really conjecture that we know little, because the point is that just knowing the topological data, constructing algebraic delta is extremely difficult, and that's why this conjecture is extremely difficult to handle it. Okay, but the conjecture doesn't tell something about the variation, so it is good to put in family. That's why I started from a family. So, and I started to use this delta 0. So that's it. Okay. So the point that you can transport, if you take a Hodge cycle, you can transport topologically this side to any fiber nearby. I will be interested, maybe I may make a picture here. So first of all, I'm not interested in the whole parameter space. I'm just interested in a very small neighborhood of the 0 in my parameter space T. So all the statement will be here, and in some sense it will be analytic geometry, not really algebraic geometry. But at the end, most of the objects are algebraic. So this is, let's say, called, there are many names, so let's say flat section. If I have to say what is the corresponding connection. Actually, the connection is called Gauss-Manin. I don't need really this language for the moment, but or parallel transport, the other name is monodromy. So in the topological world, you can transport your cycle everywhere, and so maybe just I'll make a picture and making sure it is easier. So if you have your delta 0 at the end, you can let's say here. This the one-dimensional transportation of cycle is more visual. So when you so this you can do it for any point in your parameter space, and let me skip another figure here. But once we do it, it is natural to define Hodge blocks. So first, so I will use this notation. So topologically, you can transfer your cycle, but algebraically, I mean, as Hodge cycle, you cannot transport. So it is natural to define these things called Hodge blocks. So all T. So this, for me, this T0 will be a small neighborhood, usual topology and not Zariski topology of 0 in T. So you ask,
What is that letter?
The letter, is it V?
V delta 0 is the set of all T in a neighborhood of 0, such that this is.
It's a delta.
Oh, it's a delta. Oh, it's not.
This is delta 0 because I start from
Oh, that's a
x0.
lowercase delta and a capital V.
A capital V.
Or an ablon.
Well, I thought I put the Hodge and stuff, but anyway.
Oh, but you really want? Oh, you want to draw that? That's probably. I mean, I'll draw. Is there any?
What?
No, you want to draw it like that, kind of like half the delta thing.
Oh.
But it's okay, yeah, it was, I mean, if there's an.
Benjamin Franklin invented a letter that looks a lot like that.
Okay, let me. So for the one as it is written, this is a set. I mean, just a point file, okay. But slowly we'll see that this is analytic variety, and something more important. That's the analytic space, or let's say scheme.
So what is T and T comma 0?
This is a small neighborhood of
That's
different.
another name for the small.
I mean, just let's say small neighborhood U. Okay. It's a complex. Several complex this notation is usual. Okay.
But it's also algebraic.
Exactly. You can also take when you think about germs, stock, a sheaf, and anyway. But this is for me the analytic one. So usual. So something very important that it is in 20 minutes I will explain. This is not really a set, this is actually given by ideal. And this ideal can, as bad as any ideal in algebraic geometry, it has a nilpotent, non-reduced, and so on. And but then let's skip this one. In 20 minutes I will back to this scheme structure of this kind. Okay, so maybe just before going forward, maybe the most well-known theorem about this one is, even so that it is defined, I will draw it by analytic function and so on. So there is a theorem of Khatani, Berlin, Kaplan. At the end it says that what it says, maybe let's say roughly speaking, is V delta 0 is a branch of an algebraic algebraic variety in T. And this is a really extremely difficult theorem. Recently there are more proofs and so on, but I will need this one a little bit to translate the version of conjecture that I am dealing with the classical.
What do you mean by branch?
So the point that when you take it might be, I mean, there is an algebraic variety crossing 0. It has a lot of, it might be singular, it might have a lot of locally absolute components. So will the delta 0 will be just one of the branches. So it has, if you make analytic continuation, you will land on some algebraic set. But the point is that it's the just branch, because if you make analytic continuation, you may return back and then you will enter into a new branch, and so. But this is, since this is defined,
He is like a polydisk.
Yeah.
So is it the fact that if you take the Zariski closure of this thing, then you get something of the same dimension? Is that, can you say that?
Yeah, it is the same, because at the end, what I'm saying that there are polynomials defining this one, but together with this one, they define also this guy. So I think it will be clear.
In other words, if you look at the object in the completion, then it would break up.
Yeah, but maybe what's a good example? I mean, it must be something like this.
I know.
And then,
But are you really, so what does long branch mean in this case in higher dimension? Because you say.
oh, but maybe, okay, I'll tell you, as a branch, actually, a union of branch. So maybe I have to say union. In all examples that I will put, it will be just a branch, but in general, conflict like this must be union of a branch. But not all the branches of the algebraic variety.
Not some random point saying.
Yeah,
that
exactly.
are not, okay.
Yeah. Anyway, if you know, assuming that we know this one, so maybe I introduce the variational Hodge conjecture in this context, which, knowing this Khatani Kaplan, is the same as the original one by Grothendieck. So if Hodge conjecture is true for just one Hodge cycle in your that you started with, then it is true for all t, all delta t. So the original conjecture is stated in a more global, a family of Hodge cycles over, but one can say that the end is this version is. So the point is that if you verify the Hodge conjecture at just one point, so the variational Hodge conjecture claims that it is true for if you vary it and you go to delta t being Hodge. And the difficulty must be the same as the original Hodge conjecture, because at the end, verifying Hodge conjecture in one fiber doesn't mean that you can verify the other point.
You otherwise get the standard lectures conjecture.
Yeah, exactly. Anyway, but whenever you have a very difficult conjecture, you want to make.
So I don't understand, is it a Hodge conjecture true? You mean that the cycle remains algebraic?
No, just delta zero,
Yeah.
algebraic, but then I deform it topologically, still it is Hodge, and then the Hodge conjecture would imply that the Hodge conjecture is true. I mean, the main reason that why Grothendieck introduced this conjecture is because you can avoid topology in this
No, I
conjecture.
understand, but you see, you define this curious letter delta zero, in the locus where it's Hodge.
Ah.
So if the Hodge conjecture is true, then certainly it's irrational, then it's just the locus.
Yeah, Hodge conjecture implies.
So why say that the Hodge conjecture is true? Why not say that the cycle is algebraic?
Let me see if I.
It was maybe exactly what was meant.
Yeah, but the Hodge conjecture is a big.
It's bigger. I mean, it relies this one.
But you're just talking about this one guy,
Uh-huh.
and he stays algebraic on this locus that you call the delta zero.
Yeah, but the assumption is that I know the Hodge conjecture is true in one point, in just.
Yeah, I understand.
No,
But-
but the point is that the Hodge conjecture is a general statement.
Yeah.
See, we say if delta zero is algebraic, then.
Okay. If that's it.
If delta zero is algebraic,
Yeah, okay.
then it remains
Okay.
algebraic on this set.
Then it is true.
Yeah.
Then let's say and maybe we write it in this way. Where is this? Raise.
Well, here's the brush right here.
Yeah, okay.
Yes. Cycle of correct dimension. Anyway, this is just a little bit to introduce the content. But let's say maybe.
Oh, I don't like that either, sorry. Because you imply that there is a family of algebraic cycles.
Okay, this is not a family. Okay.
Yeah, I mean, I don't
Let's
know.
see,
Is it, you tell me, is it going to be a family? Is that the conjecture? Or?
No, okay. Actually, what I'm saying that this is wrong conjecture. I want a little bit more big propaganda. This wrong conjecture. Alternative. When you have a big conjecture, you want to make some alternative way to a little bit analyze. So
It's the wrong conjecture because it's false, or one cannot say anything about it.
no, the point is that in many instances to verify if it is wrong or correct, it's very difficult. This is the point. And for me, it's a kind of integral Hodge conjecture. It is wrong.
Okay, so
But-
Hodge conjecture is also wrong in that sense. Perhaps it's very difficult to prove.
No, he's got a point. Let him explain.
Okay, so in this variational at the end, this detail might have nothing to do with the original algebraic cycle that you started. But let's become a little bit hopeful that at the end we can this Z0 can deform. Okay? As I said, I'm not writing the really for formation. Let's say. So this means that you start from x0 and z0, and you develop a kind of deformation theory of pairs of let's say x, and then for the formation xt and then zt of original x0 and x0. And but this is so I would say alternative because this is something that at least you can touch it a little bit.
Even this one is maybe slightly unclear because you're looking at a class of.
I start let's say I start from delta 0 and I find z0 and then I say
fix
that
Z0, and you're saying for any choice of Z0, you can deform it.
then
One
for
can
the
imagine that
formation
the representatives are not
For-
uniform as others are.
for all t in my Hodge law.
But here so the question is it zero fixed or is only the class of the zero fixed?
No, maybe in this case you still say it this way. I fix an algebraic cycle z0 in x0, then I fix delta 0, and then I look the corresponding Hodge locus, and now I want to try to understand Hodge conjecture in the for this delta V coming from V delta 0. So
Yeah, but the cycle itself, maybe you cannot deform, right? Maybe
yeah, exactly. I'm putting the examples, but it's still that you can deform. There are a lot of games you can do. Okay, maybe this is wrong. If you complain me instead of C2 put P property, but anyway, this is wrong. Maybe I start making some list. Okay, maybe the typical example.
wrong means false.
Huh?
Wrong means false.
For the reason it's
False.
said. Yeah, for the reason it's said.
My English is
No, because the previous conjecture was wrong because it was too difficult. I think this one is wrong because it's false.
Even more difficult.
okay. So for example, a very nice example that you can also arrange. Let's say you take x0. Actually, this has to do with in P3. And you start, for example, let's say degree hypersurface. Actually, KAH surface is a degree 4. You take two lines which do not intersect. And one can argue that the deformation is our space of the x0, keeping these two lines which do not intersect. So maybe I will just write the coordination of deformation of x0 together with this disjoint line. And you can also put equations, you can compute, you will see that this codimension is bigger than 2. But in the case of KAH surfaces, codimension of actually in this case, the Hodge locus is known as another left-shaped locus with surfaces, but this is one, and then you know that this is wrong.
So delta, what is delta 0?
Delta 0 is the cohomology sorry. A homology class of the sum of these, the cohomology class of the sum of these class. And actually, you can put even the coefficients.
Yeah, but I mean, one could imagine a situation where, let's see.
And then let's say I want to keep both of them. So this means that R check. Or not 0. Anyway, but something I think I would say that why it is interesting to see when it is wrong and when it is true. The point is that in this way I will get Hodge class, but constructing really the curves, it will be a kind of challenging problem. And at least for this kind of project, for me, makes the Hodge theory more computational, making it more effective. And there are a lot of examples also. I tried to gather all these examples in Hodge theory book that I wrote. But let me say, we said run another, no, we go to,
but why not to ask for possible representative such that it's deformable? I mean.
Okay, yeah. You can ask. You can also. You can ask. But the point is that the point of possible representative, there is no. I want to make anything effective. Really finding all possible representative is difficult. So I have to find one by one and try to see if I can check this variational Hodge conjecture by this.
So this is very strict in the sense that degree of x not bigger than 4, you don't have this.
Yeah, exactly.
You know, it's a different thing.
But then even if you make it very positive, I mean, at enough ample class, is it possible? I mean, to make deform? I mean, as long as it is Hodge conjecture, very.
Now maybe I put the Bloch's theorem in this context. I think this is the most successful.
That's not the same as making it right.
Yeah, this is some condition. It's nothing to do with positivity.
Right.
But I mean, more is true that can always make not deformable after.
No, it's very hard to, if you give them an algebraic cycle to try to make it deformable.
Okay, maybe I put this. I have a lot of things.
Yeah. So this is why his program is good.
Still, I will not put really the definition. So Z0 complete intersection, a local complete. Local complete intersection. And there is a semi-regularity, which is also a kind of mysterious property, regular. And if really I want to translate it in a correct way, whatever Bloch has proved, I think I have to put V delta 0 smooth. But I think one can, because I am starting from, so let's just for this, for sure, this to put also. So then this will be that, basically, I mean, you can prove the variational Hodge conjecture by deforming the original one. So, and this is also a difficult theorem. I mean, as I said, the idea that in many other examples, to prove that this is false, it is correct, they become very difficult statement. Okay, maybe. So now one example also. Let's say this is one of my favorite examples. This I will just make a picture. If you want details, then I can make it.
In the theorem, is the base is object dvr, or it's only, I think it's only over C, right?
Over C, right?
Yeah,
Okay. One of the very some strange counterexample. This one really also I can prove that's a counterexample. Maybe I will not write words, just making picture. I hope that is picture. So you take P4, P5. You just linearly embedded in P7. In P5, you have the image of the Veronese. P2, image of the Veronese mapped by degree to monomials. Then you have got two-dimensional cycle inside P7. Take a point outside P5. Make a cone. Then you will, let's call this one Z, till the other one Z. It is Z. You can consider Z inside, let's say cubic, let's say X cubic 6-fold in P7. And again, if you want more detail after the talk I can give, so I don't know, I would put theorem, that's a kind of again some computation, alternative, everything the X will be made smooth. Alternative is false for this.
Consider on X, I guess.
Yeah, it's considered like X. But that's why I from P5 I go to the P7.
Yeah.
And then I produced an algebraic cycle of dimension 3, which can sit inside cubic 6-fold. And then, and the proof of this one is actually, it's very easy. The main one that I want to reach is much more difficult, that this is false. And basically it is in this case, codimension of components of the, let's say, any Hodge locus is a statement just in this case. In this case, it is always less than 8, which is H31 of X. But codimension of the space parametrizing cubic hypersurfaces containing such cycle, let's say cubic 6-fold containing this z, and of course this z also can vary. All the situation I can put on, I can make the automorphism of P5, automorphism of P7, and then this z means all these possible algebraic cycles. This is n. It's a kind of well, I didn't begin my computer, but when you compute this one, you see that this guy has codimension 10, whereas the component of Hodge has codimension less than 8. So this means that your Hodge cycle can deform in 2 more dimensions. There is no freedom. And you will get some new Hodge cycle, and at the end, I think, for example, the question, trying to construct all the representatives of this Z algebraic. I mean, it has to do with Chow groups and so on. There are a lot of complicated issue might happen. But in any, this is also one example that I found it by accident because I was just computing codimension of all these objects and so on, and that turned out that this can be also a very nice example.
How often, when you're like computing and like a run on a computer, how often does the AHC wind up being true? Like just
I'm going to do that.
heuristically. I mean,
So now one theorem about what the truth is. Okay, now one state, actually this is a theorem of with my student. So I think the situation is for me, even for the integral Hodge conjecture is false, but I think still there are a lot of job to do when it is false, when it is even in many simple examples. So, but if you complain AHC, this is not traditional way to name a conjecture, then AHP, call it AHP. So maybe I put another theorem that it is true, which is not included in Bloch's theorem. Let's say, okay, let me know. So from now on, T will be the space of polynomials, homogeneous polynomials of degree D. I will consider hypersurfaces, and then this is degree D homogeneous polynomial, and then cutting singular hypersurfaces. This will be the family of hypersurface. I will consider this one. So for each f here, then I will have x given by f equal to 0. Its projectivization inside. So I will forget the general context. Just stay on this one.
So D is not 3. D might not be 3.
D, wait.
3, I mean, you
No, actually D can be 3 also, but because I will introduce other algebraic cycles. Actually, the one that I was explaining in D equals 3. So maybe one theorem, again in favor of this alternative one. This is, I wrote it for examples of degree and n with my students. And later my students were able to prove the general theorem. So basically maybe I explain this one. I will take another algebraic cycle. Maybe I make a picture again. Okay. I will take 2, so n is even for me. I will take 2 projected space P half. These are everything inside Pn plus 1. And I will consider the intersection. This intersection will be a projective cycle, projective space Pm. So a priori then M can be -1. -1 means that they do not intersect. And then it can be coherent, it can be a line. And let's n2 until n2 minus 2. The story of n2 minus 1 is easy, and I can explain later. But anyway, I will consider this situation, and the situation in which this guy, let's say, this sits inside X. Let's say X hypersurface of degree d. Let's say it's smooth. Anyway, since these are linear subspace of this one, you can consider the space of hypersurfaces. This basically I'm containing two linear cycles like this intersecting PM. And maybe again, roughly speaking, I can say that for generic, maybe I have to say X and m less than n over 2 minus c t minus 2 algebraic Hodge conjecture is true for x, and it is let's say here I put, let's say with this p, I will avoid the coefficients, but you can also put some integer. Okay. So what this means that the only way to if you consider hypersurface containing two linear cycle intersected in PM, and if the intersection dimension is less than this one, then the deformation of algebraic cycle, this guy, keeping these two linear cycles and deforming its cohomology, they are the same. So you cannot produce new Hodge cycle by deforming this guy. And so for example, this one doesn't follow from let's say Bloch's theorem, because the intersection, maybe the only stance would be maybe the IMPA case. When they do not intersect, then maybe you can check that the linear cycles are.
So are they semi-regular in that case?
I think so, if you use this theorem. So the idea is that for me the semi-regularity as difficult as verifying alternative Hodge conjecture. So this means that for one example I can really show you that this is the same. Semi-regularity is the same as alternative Hodge conjecture. So the difficulty is the same. I think this can be a good useful method to really produce semi-regular algebraic cycle. And so anyway, this theorem says that you don't have any hope to produce new Hodge cycle by deforming the cohomology class of this guy. So, but it's still this theorem.
When you say to produce new Hodge cycles, you mean Hodge cycles that are not algebraic?
Hodge cycles which are not, you cannot verify
you get from that
by deformation of this guy.
Yeah, sure. That you don't get from.
So one idea of the project is exactly really is that producing more and more Hodge cycle for hypersurface. This is very difficult. The classical example due to Mumford, where there are abelian varieties, and at least you don't have equation. But for hypersurfaces, producing Hodge cycle is extremely difficult. And the idea is that I want to produce more and more, and let's see if I can play with the Hodge conjecture, not the whole Hodge conjecture, but the Hodge conjecture just work one Hodge cycle. This is which can be also a very difficult job. And so now let's a little bit keep the detail. So there are a lot of cases popping up. Maybe since I don't have too much time, I will skip. So the point is that cubic hypersurface and the intersection n2 minus 2, n2 minus 3 is not included in this theorem. And there is a reason why this is this is not included. So okay. This case, for this case, one point another representative of e squared plus So the idea was that actually you have to consider all the algebraic cycles representing the same cohomology line. So this case also is nothing mysterious, but you have to modify your algebraic cycle, you get another algebraic cycle. I think even writing a kind of this theorem in this case, it's still one needs to work, one has to work. But for the rest of my talk, I want to focus on just d equal to 3, n is and m here, and I'm a kind of obsessed to prove that the alternative Hodge conjecture is wrong in this case. But to prove that it is wrong in this case, I'm going to show some computation that at the end it is difficult. I mean, it's not easy. Okay, so maybe maybe that's so the rest of my talk, let's conjecture on top of conjecture. I want to the evidence for x en. I cut the coefficients, but you can put also the coefficients, doesn't matter. And then x cubic hypersurfaces, and then these two linear cycles are inside X, and then they intersect each other inside P and
What are you saying?
sorry. And okay, so let's try to do okay. Let's say why this case might be interesting. So let's come back to. So
n has to be n has to be like I guess yeah, at least four, yeah.
yeah, exactly. And
I mean,
That's-
no. And actually, for cubic hypersurfaces, it is the conjecture is not. So this is let me say in this case. No, I can start from 4, but this.
What do you mean for is you don't know? Like you mean for four?
No, for 4 we know the Hodge conjecture, but it's still it's still the alternative Hodge.
Yeah,
It's,
separate, yeah.
you can say that's true or not because it just has to do with deformation.
Or
In the-
can we, just for purposes of our own mental process, can we fix a particular example that we can focus on? N equals, are you're
Okay, let's focus on the sixfold. I mean, this is
Yeah.
also
yeah, so that's
2,
3.
3.
It might be better to focus on because you know the Hodge conjecture, but you don't know this.
Sixfold?
No, I'm just saying I'm making a dumb comment. Probably I should
3. Check.
Yeah, oh yeah. No, I mean, no, it's not totally dumb comment. Because we know the Hodge conjecture
Well,
for n equals 4.
okay.
It's kind of interesting in that case. Because you know that it's going to all work out in the end.
Okay.
So this is in piece, in
In the
P7.
X is 57. But the strongest evidence that I have that this might be interesting to analyze the Hodge conjecture is actually start from dimension 10. Maybe okay. Anyway, let's. So I promise that this guy has a structure of analytic scheme or analytic space, and then actually it's ring of function. I write it this way. So let's say. ideal giving delta 0. It's a sometimes something like that. It is F1, F2. I have to skip some detail. Fi. So these Fi's are holomorphic function on T0. So we can find holomorphic functions. These are let's say this is the germs of holomorphic function, not algebraic function. Then you have, and actually Fi's, one can write it. These are integrals. I will not write the precise formula, but the structure is something like that. You have some monomials, x0, beta 0, just to give an idea of what kind of function these are. And then you have this xi, this differential from xi, let's say minus 1 to the I dxi hat is a wedge product of all the xi, removing this I, and then you have to make a division over, well, sorry, there is, I used f twice, call this one g. Anyway, natural function which gives you this v delta delta, they are analytic function, and how they are given? They are given by the integration of Griffiths spaces of the complement of the hypersurface in Pn+1, and then you integrate all this delta. So this must be a homogeneous such that you transport. Maybe I have the GIs are of the form.
What is K here?
So K is the power of F, the hypersurface, such that the degree K times the degree, this one becomes the degree of the nominator, such that you can transport this differential form to the projective space. You will get, this will give you the elements here, Pn+1 minus hypersurface. And then you have to take a residue, and then you go to the H and the round. Maybe I have to write actually the residue also. I want to keep it, and then there will be a residue map that you go to X, and actually it is primitive part. And then you start integrating your topological site.
But you want to put some bound on K so that you get the right Hodge.
Yeah, exactly. Well, exactly. But what I'm saying that once after Griffiths theorem we know the Hodge filtration of the hypersurface and so on, you will collect a bunch of these differential forms.
Not all.
Not all. Not all. This will actually, it will give you in F, let's say F and 2 they have to lambda and F and 2 H and around X. Anyway, I'm skipping this all these theorems of the Griffiths, but not all differential, but you take a bunch of them, which has to do with the Hodge filtration. You integrate our topological cycle, you will get holomorphic functions. They are really holomorphic functions. They are not at all algebraic functions. And then the zero set of this set is basically the d delta 0. And more importantly, the zero, it's not just analytic variety, it's given by this natural ideal. And most of the time we are just know this ideal, not really the analytic variety. Anyway, I am skipping all this business that Griffiths and people around him started around 1980s. But the moral of the story is that this has a schema structure, and then this will affect our job. And why? So first evidence. So first evidence would be that dimensions. Again, some computation for dimensions. Let me understand what is the. So, what is the GT check?
What is the evidence for? It's, evidence for the conjecture.
T-check will be the space of hypersurfaces containing such a pair. So this will be
So what's the degree of x in your case?
it's only it is degree 3.
Just 3 or just 3?
Huh?
Only 3.
Yeah, 33. I'm focused on degree 3, and then after Bloch's suggestion, I focused on just dimension 6.
It seems the Hodge conjecture are true for this.
No, for cubic 6-fold also it's not. No, there are some, I think, one result of terrasoma in Japanese, but for some it's with some condition, but it is still open in this context. Even so, that its Hodge number are very similar to surfaces, but I don't know. Maybe James.
What is that? Is bigger than T naught V delta? Should it just be V delta? I mean,
Okay.
Codimension. Oh, that's a comma.
Tangent space of V delta 0 at 0.
Okay.
Compute the codimension, and then compute the codimension of the space of hypersurface always degree 3 dimension 6.
It doesn't depend on what T0 what the 0 is, or you take the 0 to be a Fermat.
Let me tell you that. Okay, in this let me say in this case, okay, that's 0. Okay, to be honest, I have to say that from now on also this x0 is the Fermat. And since I'm in this second expression, x7 to the 3 equals to 0.
And what are the two linear spaces?
Exactly. In this case, you can factorize x0, for example, this one with this one, and then you can get the linear space. Okay, I have to say that also this 0 and then the corresponding coefficients are specific. Maybe let's say in this case, 1 P3 will be x0 minus zeta 6 root of unit x1 equal to 0, and then you okay, maybe let's see, and then other could be doing a similar.
And the point where they meet is what?
Huh?
Where's the point where they meet, the two?
Okay, then I think this really doesn't depend on this one, but let me write in let me write a P. There is no space there. So P3, the first P will be x0 minus zeta 6 x1 equals to 0, x2 minus zeta 6 x3 equals to 0, x4 minus zeta 6 x5 equals to 0, and then let's go the x6 minus zeta 6 x7 equals to 0, and the other P3 I will keep all these, well, not, let me say, I want a point, I have to remember. If I want a point, this means that if I make different roots of unity, it will be non-infinity, so I have to keep one of the lines in common and the rest different. So maybe for other one, I have put here to the 3 up, and then to the 3, and then I will get the equations of the other picture. Okay, 5 minutes. Okay. Anyway, so some computation one has to do. So if T-check is the space of cubic 6-fold containing 2P3 intersecting in a point, if you compute dimension explicitly, you will see that this happens. But this is not at all a strong evidence, because this is the tangent space of the scheme. And it doesn't, if your scheme is reduced, smooth, and so on, this is really the dimension of V delta 0. But we are computing the tangent space of the scheme, not the algebraic analytic variety. And so for, and maybe I have to say that all these computing tangent spaces and so on, this goes back to the practice around 1980s, this instant variational Hodge structure, plus computing the cohomology class of algebraic cycle. which I have to do
So,
with.
so you don't know that the locus is smooth at that point.
At all. There even I don't have any example of which is singular. This is actually when I was consulted Pierre Denis about this one. I mean, it is still clear if we have an example of Hodge locus which is singular. This might be a very complicated algebraic cycle which makes the Hodge locus singular. I mean, but all the examples here, I can say that they are smooth. They can be not as smooth as you consider the global Hodge locus, where because of all these branches and so on. But locally they are smooth. Okay, maybe for 3 minutes. Okay, maybe in 3 minutes. Just time to say.
Wait, the one thing, okay, I'm gonna move. When you say the codimension of T naught of V delta naught, you mean the codimension of the tangent space at the origin?
No, in this case, the codimension of T check itself, because it is, you can count the parameters.
No, on the left-hand side, I think I get, that's the codimension of T check inside all of T.
In those of
But I'm not sure, I'm not being dumb about what the T naught, V delta naught.
V delta, okay, V delta is
Codimension
analytic, right?
of
It's
what?
given by ideal.
Yeah, yeah,
I compute its linear terms,
yeah.
and the linear term will give you the tangent space, and then I compute the codimension of the tangent space. Tangent space lives where? In the tangent space of T.
The whole thing,
Yeah.
okay, that makes sense. But then, so the more singular that thing is, then the lower the codimension.
Yeah, exactly.
Oh, so you're saying that knowing that it's bigger than something that might be very singular now.
I missed the eraser again. Where I put?
You don't know, for example, could it be that codimension is just zero? Could there be that?
Actually, there is most of the Hodge cycle, this guy is just point. This actually is a kind of statement I produced in my
You mean
book.
a reduced point or?
That's just point. For
reduced
me.
point?
Huh? Reduced point. This is
Oh.
I think I can think about it, but I think but topologically it's just a point. It means that it doesn't deform at all. Okay, maybe 2 minutes.
I'm sorry, once again, so your formula, I think the formula of your computing ideal is, so for the formula you should, I mean, it is a data 0 and the FTT should be in the F, right? For me, that's make more sense.
Which one?
But so you are computing the Hodge loci, right? So I guess so, maybe it's the same. For me, it's a data 0 and the F should contain the parameter T. Is it correct?
Yeah, exactly. This F, what I'm saying that then this F depends on the hypersurface, so this is
T, and then you fix your data 0.
Yeah.
Okay.
But these are,
You-
let's say,
you
I'm
look
taking
into
global
analyze
section
that.
of the cohomology bundle, which produce correct part of the Hodge filtration, which gives me the definition of the Hodge
So
cycle.
just like, yeah. And you show this smooth at that point.
Okay, maybe let's say 2 minutes. I have 2 minutes. Then I speak. So maybe
Can we do this totally dumb thing, but say that if I don't like the codimension, can I just write dimension and reverse the order that they make on me?
You could.
I mean you can do
Yeah,
it.
I don't care.
Fair enough. What's the?
But
But the codimension is a more natural number. I mean because the parameter space of all this.
I don't know, I'm having an issue with the codimension, but because then I don't have to worry about where it is. It's the dimension. I just, but it's equivalent to if I want to think about it like dimension,
Yeah.
it's like totally correct. Good.
Okay,
I'm gonna do that.
so
Go for it.
maybe this one. Well, this is not include the article because it is a very ugly Taylor series that I have to invent in the last 5-6 years. But let's say this. Let's say well, I have a text in a book, a book that is in my webpage. But in any case, the content of this let's say section 85. So this is maybe I come back to 5. Writing explicitly in a closed formula the Taylor series. For which example, I will take the Fermat and I will start to perturb it with for the moment, all possible models. So the center will be the Fermat, and then degree. This is general for hyperthermal. So something for my surprise that it is possible to write down a closed formula of a Taylor series of periods of the Griffith spaces of the de Rham cohomology. I mean, the residuals. And these are generalization of, let's say, all these Gauss, starting from Gauss hypergeometric function, all most of these hypergeometric functions that you can realize them as a period. But the point is that this is difficult because you start from hypersurface that at that period is a number and its function. And it turns out that you can write it down this series. Next step, I don't know how to handle this the Taylor series theoretically. So I implement in a computer. Computer. Since I have closed formula, I have a lot of program for commutative algebra. I use singular. Of course, the computer doesn't understand Taylor series until the end. It just understands polynomials. I start truncating all these series. So I introduce V delta 0 n. V delta 0 n is just a variety, a scheme obtained by V delta 0 after truncating n's power. After truncating at degree n. And just imagine that this Taylor series, the number of variables is just the number of parameters that you use. And by some argument, then I have to reduce the number of parameters to some smaller one because in general, and what actually maybe, let's just in the context, theorem. So, just in this case, the one that V14 delta 0 is smooth. This is no algebraic scheme.
What does it say, 14?
14 means that I approximate
Oh,
these
V14.
integrals
Oh,
until
V14.
14
Okay,
degree
yeah.
14. And when the dimension goes up, I have to reduce this 14, and in the case of cubic 12 fold, I have to go just 3 degree 3, but it's still smooth at 0. But the point is, this means that all this approximation of my original analysis scheme until degree 14 series in T alpha indicates me that this guy, this guy is smooth in the scheme theoretic sense. This means that it's also reduced. This means that most probably, exactly, your Hodge locus, the set theoretically is bigger than this T check, and then you get your Hodge cycle. I don't have time, but
Smooth when you truncate.
truncate until degree.
Wouldn't that kind of mean it's like completely smooth? I might be being dumb here too, but like if it's defined by a bunch of equations. right?
Defined by a bunch of holomorphic functions, then write down the Taylor series,
Yeah, and
and then truncate.
but don't those higher order terms like not really?
It could be obstructed
Okay.
in degree.
Exactly. I mean, at the end of the day, as I said, this is just what I'm saying that as far as I put in the computer.
I mean, the infinitesimal deformation, you go step by step, but nobody tells you, I mean, at least without some further result, nobody tells you that you might run into an obstruction in degree on.
Well, we're writing down a bunch of how are you doing it? Like we're writing down an equation for V delta 0. We have like some. That's what's happening, right?
No, the equation I have, it is given by the zeros of this bunch of integrals.
Yeah. Yeah.
But these are the analytic equations.
And 0 is in this thing.
Zero
is
is
in
yeah,
that.
yeah. 0 is the Fermat actually. 0 represents the Fermat. And actually the cycle is represented by this 2p3 that I wrote there intersecting a point and so on.
So when we take like the derivatives of this thing at 0, right? Like the gradients of all these guys, right? It's not going to really matter what the higher order terms are. Like t to the.
So this is the tangent space. I mean,
Again, I mean, you're in a situation where you're just computing infinitesimal.
Yeah, exactly. Anyway, I'm done.
But let me ask you before we run out of time, I mean.
Sorry
for.
Ah,